Hello everyone. In this video, I'm gonna basically demonstrate this part, how to set up your this like output table for your portfolio, and especially for some of you guys are still confusing during the class period about the portfolio weights optimizations set up using solver here. So this is the goal for this video. I'm gonna basically demonstrate how to get this table done correctly. Okay, so basically at this point you should be able to do your descriptive statistic and correlation calculations in Excel. Again, let me remind you, you have to basically calculating this table by yourself, and all same thing to the correlations. And then for my case here, I only have three inputs for my portfolio setup. So that is why I hard coded this part. There are 252 trading days. Total weights for my portfolio for everybody's portfolio should be 100%. For my demo file here, there are only three components. And when I create these files is back to March. So the risk-free rate back then, 10-year treasury yield is 4.25. You have to use like the rate that you find it when you start your project, okay? And these are the standard deviation that I got it. I calculated from my descriptive statistic tables here. I basically just transfer those values here. And then you have to create your variance covariance matrix. The reason you need this is because you need to use the formula to calculating the portfolio daily standard deviation. I didn't mention that. If you use stdev function to get this one, you're going to lose points, okay? So once we have this set up, now let's starting with the equal weighted portfolio. So for this one, we're gonna just calculating the weights for my portfolio. Since I only have three components, I'm gonna just using the total weights here. I'm gonna anchor that divided by my total number of components, and same idea, I'm gonna anchor that. And of course, if we equal weighted for three components, it will be roughly 33.33%. And since I anchored both numerator denominators, so all three gonna be the same weights, and you can double check the total weights here. Again, the total weights should be 100%. That's gonna be one of our constraints when we do the optimized portfolios there. So we take them together. Now we have the weights set up. So in order to get average daily return, you have to go back here. You see, I already set up the column for my demo file here. I'm going to calculating this column will be the equal weighted portfolio return. This column will be optimized portfolio with the max return and same discount, same risk. This is the optimal portfolio with the same return with minimum standard deviation, which is the risk. This is the one with the maximized Sharpe ratio. Make sure read the guideline file, okay? You need to understand why you calculating these three ratios, what is the conditions or constraints for a three optimized portfolio. So first, let's calculating equal weighted portfolio return. This is where, like you can solve this like a column one by one. I don't want to do that. So make sure that you lock the certain inputs in a specific way. So for my equal weighted, it's always going to be the weights. I use the weights this one, and I'm going to use the same weights to calculating the next portfolio for Apple, next portfolio for Apple, next portfolio for Apple. So meaning that if I use the same weights, that will be the same row here. So I'm going to basically lock the rows here for my weights, and then use that multiply by Apple's return. And this is the one, once I calculating the next column, I still gonna link back to this Apple return for the first components. And the third column still gonna link to this column for Apple returns. So what I'm gonna do here, I'm gonna basically just lock the column D here. So you see the weights is locking the row, return is locking the column. And you do the same thing for another two components in my demo files here. For your case, you're gonna have 8 components there, okay? So we have returned this one plus the weights for the mutual fund. I'm gonna lock the row for this one and multiply by the mutual fund return. I'm gonna lock the column for this one and the plus. The last weights for my Bitcoin here, I lock the row, multiply by the Bitcoin return, which is F5 here. I'm gonna lock the column here. Now I'm done with this one. So then I can basically just highlight this column, copy this formula down, So I'm going to basically just highlight this entire column, copy this down. And once I copy this down, since I locked the things that I supposed to lock in the correct way, I can just go ahead, copy this formulas to the right to get all three other optimal portfolio return calculated. Right now is zero, which is right because I haven't set up the weights for them yet. But the calculations are setting up correctly, so I don't have to worry to come back to redo this return calculation. Once I got this done, I can come back here to my table, continuing working on the equal weighted portfolio statistics here. So first one, we want to calculating the average daily return. Then we just using the average functions, go back to find the equal weighted portfolio return, highlight the entire column, close the parentheses. This is my average daily return. And then the next one, we're going to annualize this. Basically, you use a 1 plus your daily return to the power of a number of trading days. I'm going to lock this trading days is because I'm going to using the same one for next three columns there. And then -1. I got my annualized return for equal weighted portfolio. Standard deviation, I did mention, do not use STDEV. Instead, you have to do the matrix multiplication calculations to derive standard deviation. So first, we have a square root, and then we use the matrix multiplications. First, we're going to do a matrix multiplication between the transposed weights and the variance covariance matrix. So that is why we retype this MMULT matrix math multiplication functions here. First, we're going to transpose the weights, close to parenthesis, comma, and we use that to multiply by the variance covariance matrix here. I'm going to lock this one because when I copy this to the right, we will let weights change, but we do not want to change the variance covariance matrix there. Close to parenthesis, comma, we're going to multiply by the actual weights vectors again. Again, we will let this change so you do not have to. Okay, I think I got this one. I should be transpose the weights here, not transpose the standard deviation. Okay, so transpose the weights, multiply to the variance covariance matrix, and then multiply by the actual weights vectors here, close to parenthesis. I got my portfolio daily standard deviation calculated. Once I got this one, we just have to annualize that, use that to multiply by square root of the number of trading days. Again, I'm going to anchor this number of trading days. Pay attention how I lock certain things is because eventually I'm going to copy all these formulas to next three columns before we do the optimization. Then Sharpe ratio, basically that's just annualized return minus the risk-free return that I picked there. Again, I'm going to lock that risk-free rate divided by my annualized standard deviation. I get my Sharpe ratio. Then we need to get the trainer's ratio. In order to get that one, we need calculating the beta first. So the beta, we basically running regressions using the equal weighted portfolio return against the benchmark return, which is SPY. So we use a slope function, go back to the return, find your equal weighted portfolio returns columns here, this one, comma, and we're going to run the regression basically against the market portfolio return. This is the SPY return. Highlight the column, and we're going to lock this column for the calculation. The reason we're doing that, I'm going to come back. You see, I'm running the regressions between the portfolio return and the market return. The reason I lock the market return in the slope function is because I'm going to copy this formula to the next three columns. But we will let the return for the portfolio change since different column represents for a different portfolio. Once we have the beta, now we're calculating trainer's ratio by using the annualized standard annualized return minus the risk-free return. Let's anchor that and divided by the beta, we get a trainer's ratio. Okay. Once you get the equal weighted portfolio static assessment done, we can basically just copy this entire column and then we're going to paste the formula. Do not paste the value, we paste the formula, or you can right click your mouse to paste the formulas there. Okay. Now we're done the setup here, and apparently all four columns are having the same result, which is not right. But besides the weights, everything else, the calculation should be same. And now if you go back, since all the setup are the same for four columns here, all the returns for four columns should be the same. for now, okay? The end, the result should not be the same. So double check, see if this is the situation for now. Now everything's set up correctly. We're gonna starting to do the optimization. This is the part, again, go back to check the guideline file. Make sure you understand what is the constraint for each individual optimized portfolio. So the first one, what we want to do is basically we want to maximize this one. We want to maximize, I'm gonna just highlight that, maximize the average return for the portfolio while we maintain the same risk as the equal weighted, okay? So the condition constraint for this one will be keep this risk the same as equal weighted, but let's see if we are able to increase this return by changing the weights. That's the goal here, okay? So if that is the goal, then what we're gonna do is, I'm gonna just put it this way on the bottom so you won't be confused about my highlights here. You do not have the highlights in your reports, okay? So basically this yellow means this is our objective for optimization, and this is gonna be our condition or constraint, okay? So let's get started. Basically for our solver, we're gonna go to data, click solver, and once you see the solver windows here, let's just reset everything. So first of all, what is the objective? Our objective, let's reset everything. Our objective is this one, is our return for this maximize the portfolio here. What we're gonna do, we want to maximize that, okay? Maximize the return by changing the weights for all of your components. And now we're gonna starting to throw in constraints here. First, let's add the first constraint. So the first constraint is we want to make sure that the standard deviation, which is the portfolio risk, will remain the same as your standard deviation for your equal weighted portfolio. So again, this optimization, we want to check keeping same risk. Are we going to be able to increase the return by changing the weights? So this is your first constraint. Once you get the first constraint done, then we're going to add the second one. So the second constraint will be this total weights should be equal to 100%, which is 1, okay? This will be our second constraint. Then we're going to add a third constraint, also mentioned in the guideline file. Since you already pick your components there, I know sometimes it will be optimized by get rid of certain components, but let's say like we already done our due diligence. We make sure that all of that will be helpful, and we do not want to get rid of any components. So meaning that all of the weights for all of your components should be greater than 0. There's no, if you check this one for the constraints here, there's no strict greater than or less than. So then how can we do this? Basically, what we're gonna do is we're gonna just throw in some, like a more like a hypothetical assumptions there. We're gonna assume all of these weights gonna be greater equal to 0.0001, which gonna be like a 0.001%. Okay, so meaning that we have to give some weights for each individual components. There's no components you're gonna basically get rid of that since you already pick all of that. Okay, so if this is the case, let's click OK. Now we're done with all the constraint specifications here. Let's click solve. And now you see that my weights changed. And let's just go ahead, keep the solver solution, click OK. My standard deviation remain the same compared to this portfolio, but you do see your returns is increased by changing the weights for my components here. So instead of doing the equal weighted, if we give these weights, you're going to realize your return going to be able to bump up and while maintaining the same risk. Okay. Oh, I'm sorry for the typos here. This should be a return. Okay, so this is how you do optimizations under the first optimize the portfolio, keep the same rate, same risk, while increase the return. Now we're gonna move to the second one. This is called minimum standard deviation. So what we're gonna do here is now our objective cell becomes to the standard deviation, which is the portfolio risk. We want to make sure this one is minimized while we maintain the same return as your equal weighted portfolio. So we want to keep the same return, but see if we can change the weights to help us to reduce the risk. Okay? So now we're gonna basically just go to data solver again. So under the solver, let's just reset all, get rid of that. What is our objective? Values or sale for this second optimized portfolio. Now it's gonna be a daily standard deviation. This is our objective sale, and we're gonna minimize that by changing the weights. So now we're gonna add constraints here. So the first constraint, again, we want to minimize the risk by maintaining the same return. So meaning that your daily return should be same as your equal weighted portfolio return. Click OK. This is your first constraint. Second constraint, and of course, our total weights should be equal to 1. Click OK. Now let's add another one. What is another one is basically all of our weights should be greater or equal to 0.0001. And these will be the constraints. So each of your components should have a little bit weights. There's no short settings. There's no get rid of individual components. That is why we have this constraint. Second one, total weights for all components should be equal to 100%. The third one, for this case, we want to minimize the standard deviation while maintain the same return as the equal weighted portfolio. So the return for the equal weighted portfolio should be the same as this portfolio. Now let's click solve. And you see my weights change again. Let's keep the result. And also, by the way, why these weights now is a blue color is because after you use the solver, you can see this becomes to hard-coded numbers there. That's why these are blue color. Now let's take a look. Our return remain the same, but now you compare this standard deviation, you do see the standard deviation is declining compared to the equal weighted portfolio. So this is the second optimized portfolio setup. The third one, let's go back to the data. So basically, what is the goal here? The third one, we want to maximize the Sharpe ratio. So you may wonder, well, then why there's no condition to maintain certain things change? The reason of that is because for all of these two, you have to make sure that to reach one goal while maintaining the other constraints here. But the Sharpe ratio is calculated by combining the return and the risk. So therefore, we do not have to maintain anything. If you want to increase your Sharpe ratio, we basically want to increase the return as high as possible while drive down the risk as low as possible. So that is why there's no constraint like these. You have to maintain certain things the same. Okay. Now let's go to data, solver. What are we going to do? We're going to basically just reset everything here. Now, what is our goal here? Our objective is this Sharpe ratio. We want to maximize that. I already picked that by changing the weights. Now let's starting to add constraint. Since we don't have to maintain anything to be the same, so now we only end up with two constraints here. First, the total weights should be 100%. And the second, each component should have been given a little bit weights. So this one should be greater or equal to 0.0001. Click OK. And then you click solve. Now I have my result. I click OK to keep the result. And you can see that in order to increase my Sharpe ratio or maximize my Sharpe ratio, I should give a very minimum weights to the mutual fund. I think if we, without giving that constraint to keep a little bit, I'm sure that it's going to get rid of the mutual fund. You're going to be able to increase this even a little bit higher. But again, let's just follow the guideline file, make sure you understand what are the constraints for each individual components. Now you compare this one. This one do have the highest Sharpe ratios compared to other portfolio setup. This is how we set up this like optimized portfolios by using solvers. Make sure that you set up everything correctly. You lock the correct sale in the correct way. Then this should work. So let me know if you have any questions. And this is it. Bye.